So here in this slide, we distinguish between the parameters and the statistic. As I said to you, parameter, we calculate it from the population, like the average, a population average, the population median, the population variance, standard deviation, or the proportion. All these numbers, we can calculate them from the population, and we call them parameters. But if we calculate these measures or these numbers from a sample, we call them a statistic. Our target is to know the parameter, not the statistics. But sometimes the population is so huge, so we cannot measure all the subject there. So we take a sample, and from the sample, we start to calculate this statistic. And after that, we have some other methods that let us know if this estimate is good enough to generalize it to the population parameter or not. Okay, and here we have some examples, like the sample mean. We can say it's a very good estimate to the population average mu, as you can see here. Same thing for the median. If we call the sample median M, so M is a good estimate to eta, the population median. Same thing for the variance. The sample variance is S square. It's a good estimate to sigma square, the population variance. Same thing for the standard deviation. The sample standard deviation S is a good estimate to population standard deviation sigma. And last thing is the proportion P hat. Okay, this is the sample proportion is a good estimate to the population proportion P. This is the binomial proportion. We already know that from chapter number 6, the probability of success. If you remember the binomial distribution, we have there two parameters, N, the number of trials, and P, the probability of success. So P here is the proportion or the probability of success from binomial distribution. Its estimate, it's P hat. And we will know today how we can find the P hat from the sample, okay? So what is the sampling distribution? So the sampling distribution, as you can see here, of a statistic. What that means? That means here we are dealing with a statistic, not a random variables. It's not like chapter number 6. In chapter number 6, we are dealing with X as a random variable, okay? So X here is random variable, chapter number 6, okay? But here in chapter number 7, we are dealing with statistics. We can say ST, for example, statistics, okay? Here is, these statistics are random variables in chapter number 7. Like what? Like the mean, like the proportion, like the median, like the standard deviation. These are statistics, and we need to find the distribution for this statistic, not for the random variable, okay? So this is the difference between chapter number 6 and chapter number 7. So as you can see here from the definition, the sampling distribution for statistics is a probability distribution. So it's like chapter number 6, probability distribution. But for what? These, of course, this distribution give us specific probabilities for possible values. For what? For a statistic can take, not for a random variable, X, for example. So a statistic here maybe X bar, maybe the median, maybe S, the standard deviation, maybe the proportion, P hat from the sample. So we are talking about these statistics, not X. In chapter number 6, as I said to you, we are talking about X, the random variable. But here we are talking about the statistics, X bar, the median, S or P hat. We need to know what the distribution for this statistic, okay? So as I said to you, our target is to know how close the statistic falls to the parameter. This is the very, very important question, because we are dealing with samples. These samples are just a subset from the population. And of course, we have a variation between the sample and the population. So when we calculate something from the sample, we need to know how close this statistic falls to a parameter. Because as I said to you, our target always the parameter, not the statistic. Okay? So in this case, the sampling distribution will help us to know the answer of this question. Okay? So as you can see here, the sampling distribution is doing what? It's describe the variability in a sample statistic that occurs from sample to sample. Yes, from sample to sample, or from study to another study. What that means, for example, and we will come to this example after a while again. If you have a population and you take from this population a sample and you calculate from this sample X bar, the mean, take another sample from the same population and again calculate the mean. Do you think that the mean from the first sample is equal to the mean from the second sample? Of course not. They are different values. And if you take another sample or you take 10 samples from the population, do you think that all means you calculate from these samples are equal? Of course not, they are different. Okay, so that means the statistic here, when we calculate it from different samples, becomes what? Random variable. Okay, so we need to find the distribution for the statistic to know how close the statistic falls to the from the parameter in this case. Okay, so the sampling distribution, this very important one, help us to predict how close the statistic falls to the parameter. So as you can see here, as I said to you, the sample statistic like X bar is a random variable in this case. Okay, so X bar will be a random variable. P hat will be a random variable. The median will be a random variable. The standard deviation, S will be a random variable as well. Okay? Okay. So it's so important to know the distribution of the statistic so we can answer on this question or to predict how close the statistic from the population parameter. Okay? So we will start with the sample mean. So what is the sampling distribution of sample means? Okay? So as I said to you, in our example, if you have a population, this population, as you can see here, okay, we suppose you can take all possible samples and you put them here. Of course, when you calculate X bar, the sample mean from the first sample here, it will be completely different than the sample mean in the second one. And also you have different value in the third one and the fourth one, blah, 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 to the end. Okay, so now X bar becomes a random variable. So just you have a random variable in a statistic, you have to know its distribution. How to know the distribution? If you know, find what? A graph. Which graph will help you to find the distribution in this case? The histogram. So if you start to find, of course, you have different values for X bar now. If you started to find the histogram for these values, you will find this histogram like this. So it's what? It's symmetrical. And you can approximate it to the normal distribution, as you can see here. So you will know after a while that the sample mean has a normal distribution. So the sample mean, again, is what? Has a normal distribution with the same mean of the population mean. But we have different standard deviation in this case. If the population standard deviation is sigma, so the distribution of the sample mean has a standard deviation sigma divided by square root of n. So this is the difference between the population standard deviation and the sample mean standard deviation. It's a sigma divided by square root of n. And we will see that in after a while in details. Okay. Here we have two things about the sample mean. If the population is normally distributed, which means the original population we have here is normal, so directly the sampling distribution of the sample mean x bar also is normal. But what if we have a population that it's not normally distributed? It's a different distribution, maybe skewed distribution or something like that, okay? Or uniform distribution or whatever this distribution. What is the sampling distribution of the sample mean in this case? So here we have two things, as you can see here. It's normally distributed with what? We have to know the mean and the standard deviation in this case. So you will find the mean for the sampling distribution of the sample mean is equal to the population mean, mu, with the standard deviation sigma divided by square root of n. Okay? So simply, if you have a population, it's normally distributed. So what is the x bar sampling distribution in this case? So it's also normal distribution. If the population has mean mu, so also x bar has mean mu. If the population has standard deviation sigma, so the standard deviation of x bar is sigma divided by square root of n. Simply like this. This if the population is what? Is normally distributed. What if the population is unknown? It's any other distribution, any other shape, skewed, for example, distribution to the left or to the right. So in this case, we apply something called the Central Limit Theorem. As you can see down there, the Central Limit Theorem. The Central Limit Theorem needs one thing, just one thing. This thing is to have very large sample. You have to have what? Very large sample. Most of the statisticians say that we can have a very large sample if n of course is the sample size greater than or equal to 30 observation. So what that means, if the sample size you took from the population is greater than or equal to 30 observation, in this case you can apply the Central Limit Theorem. But if the sample size is less than 30, you cannot apply the Central Limit Theorem. This is the very, very important condition to apply the Central Limit Theorem. Just you have something like that, now the distribution of x bar is also normally distributed with mean mu and the standard deviation sigma divided by square root of n. Okay, so of course the Central Limit Theorem solved the problem of the population is not normally distributed. So you can use the normal distribution to make any inference about the sample mean in this case. Look at this shape. In this graph, you have population distributions. As you can see here, the first one here, it's we call it uniform distribution or rectangle distribution. Okay. Another distribution, as you can see, this is of course all these are populations. Okay. Here you have two rectangle distribution. Okay, with two peaks, as you can see here. So this is what another different population distribution. Here you have exponential distribution, this one. Here you have biomodel distribution. Of course, it's skewed to the left because you have this peak is lower than this peak. So you can consider this as a tail, so it's skewed to the left. And you have a normal distribution. So you have here 5 different populations distribution, as you can see. Okay. As I said to you, the Central Limit Theorem has very important condition to have the sampling distribution X bar is normally distributed, you have to have n greater than or equal to 30 observation. So this will let the distribution of X bar normally distributed, this condition, okay? So suppose you have from these distributions sample size n is equal to 2, just the 2 observations. You take all possible samples from this distribution. All these samples has size equal to 2, just the 2 observations. So look at the distribution of X bar after you calculate X bar for all these samples, you will find the distribution becomes triangle. Okay, so it's from uniform distribution or rectangle distribution after you took all possible values, or samples of size 2 and you calculate X bar for all these samples, find the distribution, which means the histogram. You will find the histogram, it's a triangle like this, okay? For this distribution, when we have 2 triangles like that, if you repeat that process again, which means you take all possible samples of size 2 from this population and then construct the histogram, you will find the distribution becomes like that. From the exponential distribution, if you did that again, look, the distribution of X bar becomes, it's a part of the normal distribution, as you can see. Okay, we need just the other tail to the left. Same thing if you have here 2 binomial distribution, okay, or 2 peaks biomodel distribution. If you again take all possible samples of size 2 and define the X bar for all these samples and construct the histogram, you will find it's becomes a little bit normally distributed, a little bit, because except what the peak here. But if you have a normal distribution from the beginning, which means the population is normally distributed, whatever the sample size you have, small or large, greater than 30, less than 30, always you will have a normal distribution for X bar, as you can see here, okay? So this is the first case we talked about, okay? Just you have, or once you have the population is normally distributed, it doesn't matter if the sample size is large or small. Always the sampling distribution of X bar will be normally distributed, as you can see here. Now increase the sample size from 2 to 5, which means take all possible samples from the distribution of size 5 in this case, and then start to construct the histogram. You will find from this distribution, if you have n, the sample size is n is equal to 5, the distribution becomes what? Normal distribution a little bit, okay? Same thing for the second population. If you increase the sample size from 2 to 5, becomes a little, start to say, you can say it's close to the normal distribution, except the tails, of course. Look at the exponential distribution. When you increase the sample size to 5, becomes what? A normal distribution, except the tail. We need the tail to the left a little bit. Look at this distribution. When we have a biomodel distribution, if you have the sample size, increase the sample size to 5, it becomes a little bit normally distributed, except the tails. But if you increase the sample size to 30, look at all distributions for the sample mean, it's normally distributed, whatever the shape of the distribution up there. So this is the condition. Because of that, the central limit theorem put this condition n must be greater than or equal to 30 to guarantee that you will have the sampling distribution of x bar is normally distributed. So why we need that? Why we need to have a normal distribution for x bar? Because just so you know, the x bar has normal distribution, you can use the normal distribution tables or the function we have in Excel to calculate or to make some prediction or to make some inference, okay? Like here. In this example, we are talking about the average salary. Peter works numerous shifts as a seasonal waiter in a mountain sky resort. Experience from past seasons indicates that the salary for shift follows a probability distribution with a mean mu is equal to $150 and the standard deviation $6. So this is what? This is the distribution of the population, as you can see here. It doesn't say it's a normal distribution or not normally normal distribution, just a population distribution or a probability distribution. We know from this distribution two things. The mean is 150 and the standard deviation is $6. At the end of each winter, Peter randomly selected the pay stubs from 32 shifts he worked that season. To check how much he earned on average per shift, he computed the mean salary per shift from the information on these pay stubs. So here Peter took a sample size of what? Of 32 pay stubs. This is n. Is it greater than 30 observation? Yes, it's greater than 30 observation. So in this case, he can apply the central limit theorem. Why he can apply the central limit theorem? Because the condition of central limit theorem has met here. We have n greater than 30 observation because it's 32. Here we have some questions. Around which dollar value would you expect his mean salary per shift to fluctuate? So we need to know the mean salary. Another question, how much variability would you expect in mean salaries from one season to next season? Okay, which means you need to find what? The standard deviation of the sample mean for X bar or X bar, okay? Okay, so as I said to you, here we can apply the central limit theorem, right? The central limit theorem says what? X bar is normally distributed with mean mu and the standard deviation sigma over square root of n if n greater than or equal to 30. Okay, and that's it to you. The sample size here is 32, so it's greater than 30. So you can apply the central limit theorem. So what is the expected average of, in this case, will be equal to mu. What is the variability or the standard deviation of the sample mean in this case? Will be sigma divided by square root of n. So just you calculate these two things, you have the distribution of X bar as you can see in the next slide here. This is of course the answer of the first question about the what do you expect the mean of the salary. As you can see here, because we have 32 pay stubs, this is n. As I said to you, this is the sample size, and you can apply the central limit theorem in this case. The central limit theorem says it's normally distributed with mean mu. Do we know mu? Yes, we know mu from the population distribution. From the question here, he said what? The salary for shift follows a probability distribution with mean mu 150. So same value will be for the mean of the sampling distribution of the sample mean. So it's mu equal to 150 again. What about the variability? What about the standard deviation of the sample mean now? So this will be the answer on the second question. What is the variability? Would you expect that the mean salaries from one season to another? So that means you have to find the standard deviation of the sampling distribution of the sample mean, which is sigma divided by square root of n. Okay? So, do you have sigma? Yes, we have sigma. We have the population distribution here said sigma is equal to $6. Okay? And from the central limit theorem, the standard deviation of the sample mean is sigma divided by square root of n. And we have n, the sample size, 32. So all you need just to divide 60 by square root of 32. Don't forget a square root down there. Okay, so it's $10.6. So this is the standard deviation of the distribution. So to adjust this, okay, let the standard deviation here is equal to 60, because I don't want to change the value there. So it's 60 here, $60. So the standard deviation sigma is 60. So now 60 divided by square root of 32, it's 10.6, okay? So this is the standard deviation of the sample mean in this case. Okay, so this of course will let us make some conclusion. What this conclusion? First of all, we know that the sample mean has a distribution. This distribution is normal with mean 150 and the standard deviation 10.6, okay? And we can draw it like this. So this is the population actually. This is the curve. This curve is for the population distribution when sigma is equal to 60, as you can see here. But the sampling distribution of X bar, the sample mean, as you can see here, it's a normal distribution with mean 150, the same mean of the population distribution. But the standard deviation is different, okay? It's 1060, which is 6 divided by square root of n. And of course, the sigma here, divided by square root of n, sigma is equal to 60 from the population. So as you can see here, it's normally distributed. You can use it to make any inference about the salary, or in this case. This inference, maybe you need to calculate any probability. Like what? What is the probability that X bar, the mean of the, or the average salary, is less than 115, for example? Okay, so maybe in another season, Peter wanted to know what is the probability of average salary less than $150. He wanted to predict this. So he can apply now Z, because it's YZ, because it's normally distributed. So you can change X bar to Z. How? It's X bar minus mu divided by the standard deviation of the sample mean, sigma divided by square root of n, not sigma in this case, which is 10.6. Okay, so that means you will calculate the Z value, 115 minus 150 divided by 10.6. So now you can know Z for 150. And from the table, you can find the area under this curve, okay, which represent what? The predicted value, the probability that the average salary will be less than 115 in another season in this case. Okay, we will come to this part after a while, because we have to know how to apply the central limit theorem on some application. Okay, so in here the sample size has a great effect on the standard deviation. Of course, look at the formula here, sigma divided by square root of n. What that means? Sigma here is constant, right? Because we can find it what? From the population. Or it's a given sometimes. If we don't know it, okay, sometimes it's a given. But we can change n, the sample size, right? So what will happen if we increase n here? What will happen to the entire fraction? Because this is a fraction, it's a sigma divided by square root of n. It's a fraction. If you increase n here, what will happen to this fraction? Will decrease, right? And of course, is it something good or bad? It's something good. Why? Because you make the distribution less variability. If you increase the sample size, that means the standard deviation will be lower. That means the distribution is less variability. So you can make more accurate prediction or more accurate probability you can calculate, right? So it's better always to have larger sample size than a smaller sample size. And as I said to you, the central limit theorem gives us this condition: 30 observation or more than 30 observation guarantees that the distribution will be normally distributed. But if you increase the sample size more than 30, of course, it will be better and better. Okay. So as you can see here, note that as the sample size increases, what will happen to the denominator? Increases, right? And then the standard deviation decreases, as you can see. So that means with larger samples, the sample mean tends to fall closer to the population mean because you make the variability is lower and lower, which means the variability around the population mean will be lower. So any sample mean you calculate from the samples will be close to the population mean, and this, of course, our target is that to be close to the population mean, because in most cases you don't know the population mean, you estimate it from the sample. Okay. So as you can see here, the central limit theorem helps us make inferences when the sampling distribution of the sample mean x bar is approximately normal. What that means? You can apply the empirical rule because normal distribution is symmetrical distribution. So you can apply the empirical rule. According to the empirical rule, if you take two standard deviations away from the mean, what is the probability around the mean in this case? 95%, as you can see here. What about three standard deviation? If you take three standard deviation to the left of the mean and another three standard deviation to the right of the mean, between or within this interval, you have what? You have approximately 100% according to the empirical rule. So you can make inferences as you can see here. Okay. Of course, when you do that, that means you have here all possible values of x bar that will be close to the population mean in this range. I mean, two standard deviation range and the three standard deviation range. Okay. Okay. So here, the steps of applying the central limit theorem on applications. As you can see, just you have the sampling distribution of x bar, the sample mean, and of course it's normally distributed with mean mu and the standard deviation sigma divided by square root of n. Okay. Sometimes we call it sigma x bar instead of sigma. So sigma for the population. This is the population standard deviation. But sigma x bar is what? The standard deviation or the standard error. Sometimes we call it the standard error. Okay? The standard deviation for the sampling distribution for x bar. Okay? So this two symbols to know what is the difference between the standard deviation from the population and the standard deviation from the sample, the distribution of the sample mean. Okay? As I said to you, just it's normally distributed, you can find any probability from the normal distribution. So for example, suppose you need to find the probability that x bar is less than a specific mean. Say this is small x bar. So you convert the x bar to z as I did before. So all you need just to subtract the mean from the sample mean divided by the standard deviation of the sample mean. And then you can use the table or Excel function to find what the probability in this case. Okay? For example, suppose people drive an average of 12,000 miles per year with a standard deviation of 580 miles per year. Okay? Suppose that. What is the probability that a randomly selected driver will drive more than 12,500 miles? So what is the probability we need to find? The probability that x greater than 12,500. Okay? Why x? Because it says what? Randomly selected driver. So here we are talking about what? And individuals. So this is chapter number 6, the previous chapter. But we have a problem here. What this problem? We don't know the distribution. Is it normally distributed or what? It doesn't say here in this example anything about the type of the distribution. So in this case, I cannot find this probability because I don't know the probability distribution I should use in this case. Okay? Okay. But look at the second one. What is the probability that a randomly selected sample of 36 drivers will drive on average more than 12,500 miles? So do you see the difference between chapter 6 and chapter 7 now? Chapter 6, you are talking about one individuals. But here you have to know the probability distribution. Is it normal or binomial or what? Okay? So you can find the probability. In chapter number 7, you are dealing with what? The sample. A randomly selected sample of 36 drivers, okay, will drive on average. So we are talking here about what? About x bar, not x. This is the difference between here and here. Okay? More than 12,500 miles. So what is this probability? The probability that x bar, because I said it's the average, greater than 12,500. Can we find this probability? Yes. Why? Look at the sample size. N here is 36. It's greater than 30. So I can apply the central limit theorem. So the central limit theorem says what? The central limit theorem says that if you have n greater than 30 observation, so the sample mean x bar has normal distribution with mean mu and the standard deviation sigma divided by square root of n. So what is the mean of the distribution now? Now, look at up there. Suppose people drive on an average of 12,000 per mile. So this is the average of the sampling distribution of x bar. What about the standard deviation? The standard deviation will be sigma divided by square root of n. Sigma here from the population to 580. Divided by square root of n, and the n here 36. So you can find the standard deviation of the sample, the distribution of sample mean, as you can see here. And now you can convert x bar to z and find this probability. Okay, so let's do this together. As you can see here, we have the mean, we have the standard deviation. So since n equals 36, we can apply the central limit theorem because it's more than 30, as I said to you. So it will be normal distribution with mean. So mu x bar is equal to mu is equal to 12,000. Okay? And the standard deviation will be sigma x bar is equal to sigma divided by square root of n. So we have sigma 80 divided by square root of n, 36. Okay? Use your calculator to find the standard deviation of x bar. So we have 430. So this is the standard deviation of the sampling distribution of x bar. Okay? Now, convert x bar to z. Do you remember? Z is equal to what? X bar minus mu x bar divided by sigma x bar. We already calculate that. So x bar here is 12,500 minus the average 1,200, 1,000, sorry, I said 1,000. And the standard deviation of x bar is 430. So now z is equal to what? Use again the calculator. So you have here 500 divided by 430. So it's 1.16. 1.16. 1.16. Okay? So the probability we need to find, the probability that x bar greater than 1250 is equal to the probability that z greater than 1.16. Of course, if you draw this, so you have 0 in the middle, 1.16 is here, and you need this area greater than. Okay? So to find this area, you can apply the complement rule. 1 minus probability that z less than 1.16. Why we do that? Because the table will give us the area to the left, not to the right. So we can find this area from the table. And we know that all area under this curve is equal to 1. So just so you know this area, subtract it from 1, so the remaining will be what? The area we need here to the right. Okay? Same thing as we did in chapter number 6. Same thing. So all you need, you will go to the table. Let's go to the normal distribution table. So we have 1.116. Divide it into 1.1 and 0.06. 1.1 is here, 0.06 is here. So the intersection between this row and this column give us 0.877. 0.877. Of course, this is the area to the left. Okay, 0.877. So we have here 0.877. So this area from the table 0.877. Okay, but we need the other area, so you have to subtract it from 1. Okay, so you will have the area to the left, and of course the probability that x bar greater than 1200. So we have 0.123. This is the area 0.123, or you can say 12.3%. So this is the probability that on average, as you can see the question here, on average, we can say 12.3% on average. 36 drivers will drive more than 12,500 miles based on these calculations. Okay, so we can say here based on sample size of 36 driver. Okay, so this is, as I said to you, the sampling distribution of the sample mean and the central limit theorem. Same thing we can do with the sample proportion, okay? The sample proportion, or p hat. Okay, as I said to you, the sample proportion, or P, is what is the probability of success from the binomial experiment. Chapter number 6, if you return it to the binomial uh, experiment or binomial distribution, you will find that we have there two important information: the number of trials N and the probability of success P. But of course, P is the population proportion. In most cases, we don't know it. We have to estimate it from the sample. So you have the sample proportion P hat in this case. Okay? So how to find P hat? It's so easy. It's X divided by N. What is X? Binomial distribution? The number of successes. X is number of successes, and the N, number of trials. So if you return it to the binomial distribution, okay, you can estimate P hat, the proportion or the probability of success by this case. X, the number of successes divided by the number of trials. Okay. So with the same way, we need to know what is the sampling distribution of the sample proportion P hat. Okay. So again, according to the central limit theorem, you have to have, of course, N is so large, okay, and you will know after a while N should be how much in this case, okay. So you will find it that P hat is also normally distributed with mean P, the probability of success, and standard deviation, square root of P times 1 minus P divided by N. So it's similar to X bar. X bar, according to the central limit theorem, it's also normally distributed with mean mu and the standard deviation sigma divided by square root of N. Same thing here. P hat is normally distributed as well, with mean P, the probability of success, and the standard deviation, square root of P times 1 or 1 minus P divided by N. Okay, so this is the mean and the standard deviation of the sample proportion. Okay. Okay. So when we should apply this? Of course, when we have the central limit theorem, can apply this. So you have to have a large N. As you can see here, if N is sufficiently large. So when will that happen? That happen if you multiply the sample size or the number of trials times P. Of course, P here is the probability of success. Or, sorry, I said or, and. It's not or, it's and. It's not or, and. You multiply again the number of trials, but this time by the probability of failure. Okay? Both numbers or both values, the result, at least 15. So you need MB and N1 minus B greater than or equal to what? To 15. So in this case, you can apply the central limit theorem in this case. Okay? So when you can apply the central limit theorem for the on the proportion or the sample proportion, if N times B and N times 1 minus B greater than or equal to 15. Okay? So in this case, the distribution of p hat is normal distribution. So you can use it again to find what any probability or any prediction you would like to or inference you would like to do in this case. For example, predicting election results using exit polls. How do we know if the sample proportion from the California exit poll is a good estimate, falling close to the population proportion? So here we have two things, the sample proportion, the population proportion. Is this one close enough to the population proportion so we can say it's a good estimate or not? Okay? So in this case, as you can see here, the total number of voters was over 9 million. 9 million here, this is the population size. This is the population size, 9 million. Of course, to know the population, the sample proportion, you need a sample from the 9 million. We will see this sample after a while, okay? So what is if we have a sample of 3,889 voters selected randomly from the 9 million? So this is our sample, okay? So from this sample, we have 53.1% said they voted for Brown from the sample, okay? Not from the population. Because we usually don't know the result after they finish the election, right? Okay. And 42.4% for white men and 4.5% for other or no answers, as you can see. So these are the result from the sample, from this sample, 3,885. As you can see here, N here is large. As you can see, at the time of exit poll, of course, the percentage of the entire voting population is unknown. We don't know it, okay? We don't know. So you can use the sample and the results from the sample to make prediction. So let's do this. When you start to do that, after you collect your sample, okay, you will start to put 1 for the people or the voters who vote for Brown and 0 for the others. And start to count the number of voters who voted to Brown and then divide it by the entire sample size. Okay? So if you remember, I said to you P hat is equal to X divided by N, right? So X here will be the number of voters, of course, who voted for Brown, because this is what we interested in, the number of people who voted for Brown, okay? And divided by the sample size, 3,889. This is the sample size. So this will let you know what is the sample proportion in this case, okay? After doing that, we found, as I said to you from the distribution, that this proportion is 0.531. And of course, this is so this is P hat. Of course, this is the opposite. This is 1 minus P hat. Okay? Okay. For a while, ignore that we have a sample. From the population, we have 0.538 voted for Brown. Okay? And of course, the remaining is 462 to the others. Okay? So look at the or we can say the bar chart for the population distribution and the sample distribution. This is the population distribution chart. And this is the sample distribution chart. Both are similar, right? As you can see here, for the people who voted to the other person, and one for the people voted to for Brown. Okay, so as you can see here, the percentage here are so close. The percentage from the population is 0.3538, and from the sample is 0.531. Why it's so close like this? Do you know why? One thing will let you know why, is the sample size. The sample size is large enough as a ZTU. It's large enough, okay? So that means your sample represented represented the entire population. So you have so close shapes, as you can see here for these two distributions, okay? But as I said to you, usually we don't know the final results, okay, after they finished, of course, the counting the voters. So this is the distribution of the population proportion, okay, from the sample, as you can see here, okay. So this, after we find P is equal to 0.538, and of course you will calculate the standard deviation, right? So the standard deviation in this case will be 0.538, 1 minus 0.538 divided by the sample size 3889, okay? And this, of course, will give you the standard deviation, okay? If you because it's normally distributed now, so you can apply the empirical rule. So the empirical rule says what? If you know the mean of the distribution and the standard deviation of the distribution, because this is, of course, like the mean of the distribution, because it's in the middle here. This is, we can say the mean mu, but I will say P because we are talking about the proportion. This is the mean of the distribution. And do you know now the standard deviation? So you can find one, if you apply the mean plus or minus 3 standard deviation, if you remember sigma, if you remember this interval from the empirical rule, okay, which is about 100% of the data within this range, okay, you will have this shape, or you will know the minimum and the maximum proportion in this case, okay? So in our problem here, you will put mu here is equal to B plus or minus 3 times P 1 minus B divided by N. You will apply that, and you will find the minimum and the maximum proportion, okay? So the minimum will be 0.514 and the maximum 0.562. Okay, and of course it's normally distributed around the mean B 0.358, as you can see. Okay. Of course, all this if we know the population proportion, but in practice, of course, we don't know it. Okay, we don't know it. So in this case, because you don't know P, P, the population proportion, we don't know it. You have to estimate it from the sample. So in this case, you will use what? P hat. So instead of P, you will use P hat in practice. And the P hat, as I said to you, X divided by N. Right? And then you can find the standard deviation, square root of P hat, 1 minus P hat divided by N. So from the sample, of course, this in practice, this is what we should do in practice, because we don't know P P is the population proportion, and we don't know it. Okay, it's unknown. So you take a sample, and from the sample you find the P hat and the standard deviation, P hat 1 minus P hat divided by N. And then you start to construct the distribution I said to you based on the empirical rule. So you can find P hat plus or minus one standard deviation to the left and one standard deviation to the right. So you will put here square root P hat 1 minus P hat divided by N. And of course, here you will find approximately 68% of the proportions. Okay. And then if you increase it to 2 standard deviation, P hat 1 minus P hat divided by N. So you will have here 95% of all proportion within this range. And as I said to you, the remaining for 3 standard deviation, P hat plus or minus 3 times P hat 1 minus P hat divided by N. And here you will have approximately 100% of all sample proportions, or you can say the minimum and the maximum of the proportion. Okay? So how we can use this to make inference if Brown will win in this election or not? Okay, something cool actually. First of all, find the standard deviation. So you have here B hat. If you remember, we find the B hat x divided by n is equal to 0.531. And now use B hat to find the standard deviation. So it's a 0.008. Now find the last interval in the empirical rule, which is P hat plus or minus 3 times P hat 1 minus P hat divided by n, which is 0.531 plus or minus 3 times 0.008. And find the minimum and the maximum number. Okay? So the minimum number is 0.507. And the maximum number is 0.557. What do you think? You have here the minimum is 50% 0.7. The maximum 55.7%. Both the lower limit and the upper limit of this interval above 50%. So what do you think? What do you expect? Brown will win in this election? Because the lower limit and the upper limit both are greater than 50%? Yes. So we can predict that, as you can see here. Okay. So we observe that all plausible values estimated for the population proportion of voters who will vote for Brown are above the value of 50%. And they give Brown a majority over any other candidate. So in this case, we expect that Brown will win in this election. So as you can see here, this is a very good way to make prediction or inference about something we are interested in. Of course, all these methods based on what? Very important theorem, the Central Limit Theorem, as you can see. Okay? So this is the end of chapter number 7.